So let us keep moving along. Okay. So another thing to talk about here. In chapter 4 of this text, it introduces the K ratio, or just simply the specific heat ratio, the K value. Right? The K is the ratio of C sub P to C sub V. Why is that? Well, we just saw in the previous problem that C sub P accounted for both the heat and the boundary work. That's, if I've got a constant pressure situation and everything else is simplified, then that's what the C sub P was kind of designed for, is to account for both the heat and the boundary work. So C sub P is always larger because it accounts for more energy than C sub V does. So C sub P will always be larger. This value will always be greater than 1. If it's an ideal gas, the difference between the two is the gas constant. Now, we introduced this concept early on. We probably won't need it again until chapter 7, so just FYI. So mention it here, and don't be surprised when it shows back up. I'm sure he uses it from time to time in the text. I probably won't mention it until we get back to chapter 7, where it comes in handy for some derivations. That's one sheet. I thought that was one. Okay. Now, for solids and liquids, the specific volume of most solids and liquids is going to remain constant for most practical applications. The most variation in the specific volume and other properties like V, U, H, and S are really going to be predominantly functions of temperature. So with that in mind, so really what happens is, because, let's do this, for solids and liquids, C sub P is approximately C sub V. Again, remember, C sub P is larger because it will account for the boundary work in an ideal gas. There's no variation in the volume. There's no expansion or contraction, at least not major expansion or contraction, for solids and liquids. So there's really no reason for there to be a difference between the two. So C sub P will be approximately C sub V. A lot of texts will simply call this C, the specific heat of the substance. They won't even differentiate, or won't even put a subscript. Your text, the Changle-Bowles text, likes to put a C sub P subscript. Okay, so we'll go with that. So what happens then is delta U essentially is approximately C sub P average times delta T. And if you need enthalpy, which we'll need for flowing liquids later on, enthalpy ends up being approximately C sub P at the average temperature times T2 minus T1, plus this other quantity, V times the change in pressure. Specific volume times the change in pressure, or change in pressure divided by density. Either one works. Okay, but this is only for solids and liquids. Different situation for ideal gases. We talked about that last time in lecture 9. This is only for solids and liquids. Okay? All right, so with that in mind, if we look at an example problem, I want you guys to start copying this down. Notes. Right on that. Okay. So I'm going to look in my notes because I'm missing a couple of values here. I'm going to see if I can find them quickly. We've got 12 millimeter stainless steel balls, ball bearings, if you will. Those are coming out of a furnace. And so we got Little stainless steel ball bearings coming out of a furnace. They're starting out at a pretty high temperature there. Okay. Starting out at 900 degrees C. They cool in the atmosphere to 800 degrees C. And so I've got some properties here that I didn't write down. I would normally on my smartboard would write these properties down. I had to go pull out of my old notes those properties because I was like, I don't have those on the slides. Here we are. Example. Given. We've got stainless steel ball bearings that have a diameter of 12 millimeters. And it's 25 millimeters would be about an inch, so they're about half an inch. They start out at 900 degrees C. They finish at 800 degrees C. They cool in the atmosphere. They have, again, I didn't write it on those slides, but they've given us the density of the stainless steel to be about 8,085 kilograms per meters cubed. They've given us the specific heat of the stainless steel to be 0.48 kilojoules per kilogram Kelvin. Kilojoules per kilogram Kelvin. Now, if you went in your text and the table, I think it's A3, where it will give you properties of certain solids, liquids, and metals, you could look and see if you have a stainless steel in there. And some texts might, ours does not. That's the reason I've got these properties here, and I give these to you separately. You do have like some kind of a mild steel or a rolled steel. That would be really close. Stainless steel has properties very similar to steel, but there are some differences. So if you used values for steel, it would get you in the ballpark. In the absence of anything else, it would at least get you started. Okay? But realistically, we'll go try to find a trusted source on the internet or something like that if we just didn't have these values, or we have a research lab that will measure that for us. Okay? Again, the problem wanted to know, find the heat into the atmosphere. So I have these red hot little balls of stainless steel. How much heat is going to the atmosphere to cool it from 900 to 800 degrees? See? Okay, well, what's a good tool we might have? And this is going to be Q out, right? So this is Q out of the ball into the atmosphere. So what's a good tool we might have to find a heat transfer value? Again, my hope is at this point your gag reflex says, Steve, that's the first law. Yes, that is correct. I've got a little ball bearing losing heat. That's it. And they didn't give us information about the mass loss. Yes, at those temperatures it's probably losing a tiny bit of mass, but it's probably not enough to worry about. I think we can assume it's a closed system, losing heat, and that's it. That's the entire left-hand side of the equation. Add the ins, subtract the outs. That's going to equal M. The energy that changes is going to be the internal energy. So M delta U. So Q out is equal to M U1 minus U2 if I distribute the negative sign over. And again, we're going to approximate that as M C sub P T1 minus T2, which I have C sub P. So we look at this. All right, I've got both temperatures. I know the C sub P. I don't know the mass. So how would I find the mass? Well, Steve, there's no equation for mass. Well, yeah, there are. I haven't talked too much about them in this class. I mean, if it was an ideal gas, we could use ideal gas law to find the mass. Okay, what else do we know? Is there anything here that's helpful? That might be helpful, right? Density is mass per total volume. Okay, I know the density, but I don't know the volume. So how do we find the volume? Well, engineering is taking all of your existing knowledge and trying to put it together to solve a problem. If you don't know the volume of a sphere, my hope is that you understand you could go look up a formula for volume of a sphere. I believe it is 4/3 of a pi times d cubed. If that is not right, feel free to blast me in the comments, but I think that's correct. Okay, so know the volume. That gives me the mass. I've got the specific heat, temperature changes, engineering work's done. I got 3 equations, 3 unknowns. And that's just plug and chug. Okay? Alright, so let's rock this out, shall we? Get my calculator up here. Don't have a lot of time to run the numbers, but I think we can get there. Okay. So the volume is going to be 4/3 of pi times, I'm going to convert this to meters, that's going to be 0.012 meters, that's going to get cubed, 0.012, that's going to get cubed, times pi, times 4 divided by 3. Very small, these are very small ball bearings. So I shouldn't expect a lot of volume. 7.238 times 10 to the minus 6 meters cubed. And that's in meters cubed. Meters cubed are enormous. Okay, the mass, we said, I said over here, that if I take volume times the density, that gives me the mass. So multiply this by the 8085 density. That means each one of these ball bearings has about 60 grams of mass. It's 0.0585585. Kilograms. Okay, so this is done. We're up to here now. I know the mass. I've got C sub P given. I know the temperatures. Just compute. The heat loss by this thing is equal to that mass, 0.0585 kilograms times my given specific heat of 0.48 kilojoules per kilogram Kelvin, multiply by 900 minus 800, those are kelvins. So multiply this by 0.48, multiply this by 100. Q out is equal to 2.81 kilojoules. That seems high. I know what I did. You know what I did? It's back here. This is the diameter. 4/3. I apologize. That is. You guys should be blasting me in the comments. 4/3 pi r cubed. So it's back here. All right. 0.012 divided by 2 cubed times pi. So notice how I have this nice, neat, and laid out, clean and orderly. So it's going to be easy to go back and fix this. 9.05 times 10 to the minus 7. Multiply by the density, that's 8085. This is 0.007315 kilograms. And multiply that by the 0.48. Multiply that by 100. 0.35 kilojoules, which matches the number I have in my notes here. So I apologize, I forgot this divided by 2. So recheck your numbers now. Okay? Now, if that's not correct, please feel free to blast me in the comments. But I'm pretty happy about that. I think that's pretty good. And not a bad place to stop. See you guys next time.